You know, when you grab a plastic jug of milk from the fridge or, say, a sealed bag of coffee beans from the pantry, there is this fundamental assumption we all make without even really realizing it. You look at that solid, thick plastic and you just think to yourself, that is a wall, nothing is getting in, and absolutely nothing is getting out.
Right, yeah. It feels absolutely like we completely trust the physical seal of the package. It's solid matter, so our brains just automatically categorize it as an impermeable barrier.
But then you take that exact same seemingly solid plastic and you put it under a scanning electron microscope, and suddenly that impenetrable wall looks a lot more like like a microscopic sponge. And you have this really jarring realization that we live in a world where things are constantly invisibly leaking right through solid objects.
Exactly. The whole idea of a perfect barrier is really just an engineering illusion. Whether you are dealing with a milk jug, a catalytic converter, or even a pharmaceutical blister pack, what we're actually looking at is just a highly controlled leak.
Okay, let's unpack this because today our mission for this deep dive is to master the invisible forces that dictate those leaks. For the listener joining us, we are looking at the fundamentals of mass transfer, specifically topic 1, which is diffusion, and topic 2, diffusion in solids from course 280.271. And the goal here isn't just to help you pass your process engineering exams, though, we will definitely get you there. The real objective is to help you actually apply these exact concepts on the plant floor.
That is a really crucial distinction to make early on. We're going to cover pure diffusion, diffusion through solid materials, which is where we get into permeability and convective mass transfer. Because if you want to predict the shelf life of a packaged product, or if you need to calculate product drying times in a factory, or design these massive separation equipment units, this is the foundational bedrock you absolutely have to stand on.
So just to start us off on the right foot, what is the core mechanism actually happening here? Like if I'm looking at a physical system, whether it's a coffee bean or a water filter, what is fundamentally driving this mass transfer?
Well, it all comes down to what we call the general transport equation. It's a very elegant concept, honestly. The rate of transfer equals the driving force divided by the resistance.
Hold on, that sounds suspiciously like heat transfer, like Fourier's law, right?
Because it is. Yeah, mass transfer by diffusion is directly analogous to heat transfer by conduction. With heat transfer, you need a temperature gradient. Heat inherently just wants to move from a hot area to a cold area.
Right.
Well, mass transfer by diffusion operates on the exact same logic. But instead of temperature, it relies on a concentration gradient or a chemical potential gradient. Particles will always move from a region of high concentration to a region of low concentration.
So basically, mass transfer is just the universe trying to balance its chemical checkbook. Systems that are out of equilibrium will always just aggressively move toward equilibrium.
That is the second law of thermodynamics in a nutshell, yeah. Imagine you have a tank with two different gas species, let's say A and B, and they are initially separated by a solid partition. The moment you remove that partition, random molecular motion, literally just molecules bouncing around, will cause them to mix.
Just from the bouncing?
Exactly. They mix until the concentrations of A and B are perfectly uniform throughout the entire tank.
Yeah.
They're constantly moving to equalize their chemical potentials.
Okay, now, in the textbook, this equalization process is defined mathematically by Fick's law. But let's try to translate that into something we can visualize. Fick's law uses this term, flux. In plain English, what exactly is flux?
Flux is simply a measurement of how much mass is moving through a highly specific area over a given amount of time. If you imagine holding up a 1 square meter window frame in the middle of a slowing gas, flux is measuring exactly how many kilograms or how many moles of a substance fly through that specific window frame every single second. So your units are typically going to be kilograms per square meter per second, or moles per square meter per second.
Got it. So if flux is like the traffic volume flowing on the highway, what determines the speed limit? Because the rate of diffusion, the diffusivity coefficient, isn't just a static number you pull out of a hat, right? What physically changes how fast these molecules can actually move?
There are three main physical factors that dictate your diffusion coefficient: temperature, the physical size of the molecule, and the viscosity of the fluid it's moving through.
Temperature makes sense.
Right? Temperature is the accelerator. If you increase the temperature, you are directly increasing the kinetic energy of the molecules. They're literally vibrating more, moving faster, and bouncing off each other with way more force, so the diffusion speeds up.
Okay, that makes intuitive sense. Hotter means faster. But what about viscosity? If viscosity slows things down because of molecular drag, does that mean mass transfer in a really thick liquid, like say a heavy syrup, requires exponentially more driving force to achieve the same flux as it would in water?
That is exactly what it means. If you increase the physical size of the molecule, or if you increase the viscosity of the fluid, you are dramatically increasing the drag.
Right.
And more drag means more physical restriction to motion, which absolutely plummets your diffusion coefficient. You would need a massive concentration gradient in that syrup to match the flux you'd get in water with a much, much smaller gradient.
If we connect this to the bigger picture, I imagine this isn't just an academic headache. Out in a processing plant, if we want to mix a liquid or a gas, we don't usually just sit around waiting for pure diffusion to do the job, right?
Mm.
We just turn on a massive pump or a giant industrial stirrer to force the convective mass transfer.
Oh, absolutely. We use mechanical force whenever we can.
So why is an entire section of this course, Topic 3B, dedicated strictly to solid diffusion?
Because you cannot pump a solid. You can't stick an impeller inside the wall of a plastic bottle or inside a solid catalytic pellet or, inside a coffee bean.
Oh, wow. Yeah, obviously.
Right. For industrial processes involving solid matrices like packaging, catalytic chemical reactions, the staling of baked goods, or freeze-drying operations, pure diffusion is literally the only mechanism you have to move material in or out.
Which brings us to my absolute favorite real-world application from the source material, espresso coffee. Pulling a shot of espresso is, at its core, a heavily engineered, solid liquid mass transfer operation.
It absolutely is. When you drink an espresso, the flavor profile in that cup is entirely determined by the differences in the diffusion coefficients of the various compounds locked inside the roasted bean.
Okay, walk me through the timeline of that extraction, because as someone who drinks way too much coffee, this is incredibly relatable. When that high-pressure hot water hits the puck of coffee grounds, what happens first?
Well, the first thing to diffuse out is caffeine. Caffeine is highly water-soluble and diffuses very easily into the liquid phase, so a vast majority of the caffeine is extracted in the very early seconds of the process.
So the jolt wakes up first. What's next?
As the extraction continues, you start pulling out the volatile oils and lipids. These are the larger, more complex compounds that give coffee its rich flavor, the body, and that aromatic crema.
But they're bigger, so they're slower.
Exactly. Because they are larger molecules, they face more drag. They have a lower diffusion coefficient than caffeine, so they take a bit longer to extract. And then finally, if you keep running water through the grounds, you start extracting the organic acids and astringent plant fibers. These are the most difficult to move, so they take the longest to diffuse out of the solid bean structure into the water.
Oh, this is a total revelation. So when I go to a cafe and the barista gives me a super bitter, harsh, over-extracted coffee, it is quite literally a mass transfer failure. Like they've given those slow-moving, bitter organic acids too much time to diffuse into the water.
Exactly. They allow the mass transfer process to run way past the optimal set point. And this is precisely why engineers and, frankly, baristas obsess over particle size, your grind size, and water flow dynamics.
Because smaller particles mean less distance to travel.
Spot on. If you grind the coffee finer, you drastically increase the total surface area and decrease the physical distance those molecules have to travel to reach the water. You are essentially shrinking the resistance, which speeds up the entire mass transfer timeline.
That is going to completely change how I look at my morning coffee. But let's shift gears from coffee beans to the bags they come in. Topic 3C deals with boundaries, solubilities, and packaging. When a gas or liquid meets a solid surface-like oxygen hitting the outside of a coffee bag, what actually happens right at that interface?
At that boundary, we use a critical metric called a distribution coefficient, which we represent with the letter K. The K value is the ratio of interfacial concentrations once the system reaches equilibrium.
The formula in the notes is K equals CLI over CI, but what does that actually mean physically? Like, if I have a K value greater than 1, what does that look like in reality?
If K is greater than 1, it means that at equilibrium, the liquid or gas phase is holding a much higher concentration of the solute than the solid phase is. Think of it like a partition. Different materials have vastly different affinities for absorbing a substance.
Give me an example.
Sure. If you soak a standard kitchen sponge in water, the sponge eagerly absorbs it. But if you put a piece of dense plastic in water, very little water actually enters the molecular structure of the plastic. The K value mathematically defines that exact balance point at the boundary between the two materials.
Which brings us back to that electron microscope image of the high-density polyethylene, the HDPE, the standard plastic milk jug.
Right. And we connect this to the bigger picture. What's fascinating here is that when you look at those structural photomicrographs of an HDPE film, it looks like a dense, tangled web of polymer chains. It is not a solid wall. Packaging does not stop mass transfer. It only slows it down.
And the overall rate at which a gas like oxygen moves all the way through that plastic barrier, that's called its permeability.
Yes. And permeability isn't a single standalone property. It's actually a combination of two distinct phenomena working together.
Diffusivity and solubility, right?
Exactly. Permeability is the product of diffusivity and solubility. First, you have solubility. That's how much of the gas can actually absorb into the surface of the plastic based on that K value we just talked about. Second, you have diffusivity. How fast can those absorbed molecules physically navigate their way through the tangled maze of the polymer chains to reach the other side?
Okay, so if I'm a packaging engineer designing, say, a potato chip bag, I don't just use one type of plastic. I use a layer of plastic for strength and maybe a thin layer of foil to block oxygen. How do I calculate the total resistance of a composite package like that? Is it complicated math?
Not at all. That is where we use the concept of permeabilities in series. The formula is simply ZT equals Z1 plus Z2 and so on, where Z represents the thickness divided by the permeability of each individual layer.
Oh, so it's exactly like electrical circuits. If I have a foil layer and a plastic layer, I'm just stacking the resistances in series. I just add the resistance of layer 1 to the resistance of layer 2 to get the total barrier strength.
Spot on. You were just adding up the hurdles the molecule has to jump over.
Okay, let's make this a little harder. What if the solid isn't a tight plastic film, but something highly porous, like a ceramic water melter, or a freeze-dried strawberry, or a catalyst pellet?
For porous solids, the math shifts because the structure is so erratic. We have to calculate what's called an effective diffusion coefficient. And to do that, you need to understand two structural parameters: porosity and tortuosity.
Let's start with porosity.
Porosity, represented by the Greek letter epsilon, is simply the void fraction. It's a measure of how much empty space is inside the solid, usually a value between 0.1 and 0.4.
So if we imagine the porous solid as an office building, porosity is like counting the number of open doors and hallways. More empty space, easier to get through. But what is tortuosity?
Tortuosity, represented by tau, is a measure of the interconnectivity, or the twistiness of those pores. It's the ratio of the actual winding path length a molecule has to travel through the maze of pores compared to the straight line point A to point B distance across the solid. It's usually a value between 1.2 and 3.
Continuing the building analogy, tortuosity is how much of a confusing maze those hallways are. A higher tortuosity means a longer, more frustrating journey for the molecule, which drops your effective diffusion rate.
Exactly. And this is where we have to introduce a crucial distinction in the physical mechanism of the flow: Knudsen diffusion versus molecular diffusion.
Here's where it gets really interesting, because the textbook makes a huge deal out of these two, but students always seem to mix them up. What is the actual physical difference?
It's all about what the molecules are bumping into. Molecular diffusion is like bumper cars. The pores are relatively large, so the gas molecules are mostly just colliding with each other as they drift through the void space.
Okay, Knudsen.
Knudsen diffusion happens when the pores are incredibly tiny.
How tiny are we talking?
Smaller than the mean free path of a gas, meaning the distance a molecule travels before it hits another molecule. In Knudsen diffusion, the molecule is trapped in such a narrow hallway that it almost never hits another gas molecule. It just constantly bounces off the physical walls of the pore.
I see.
Because the physical mechanism of resistance changes from gas-on-gas collisions to gas-on-wall collisions, you have to use entirely different equations to model the flux.
That makes total sense. Now, let's talk about the math overall, because if you were taking course 2NE80.271, you have to translate this physical intuition into formulas. We need to talk about the ideal gas law. PV equals nRT. Pressure times volume equals the number of moles times the ideal gas constant times temperature. Why is a basic chemistry equation so critical in an advanced mass transfer course?
Because on a real plant floor, your instruments read in pressure, pascals or atmospheres. But Fick's law requires the concentration gradient to be in molar density, moles per cubic meter. The ideal gas law is the bridge. Well, if you rearrange the formula to N over V equals P over RT, you suddenly have a direct way to convert the gauge pressure of a gas into its molar concentration.
But there's a massive trap here for students and young engineers, right?
Yes, a huge one. You must pay fanatical attention to the units of the ideal gas constant R. The value of R changes completely depending on whether your pressure is measured in pascals, atmospheres, or torr. Using the wrong R value won't just make your answer slightly wrong, it'll make it off by several orders of magnitude.
Yikes. Okay, let's apply everything we've talked about so far. Walk me through the actual methodology of predicting shelf life. If I'm a plant engineer and I need to guarantee a bag of chips stays crispy for 6 months, how do I calculate that without just, guessing?
It requires a logical four-step engineering process. Step one, you define your critical concentration. You need to know the absolute maximum limit of moisture or oxygen your product can absorb before it's ruined, whether that's sensory degradation, clumping, or losing its crispness.
Okay, step two. I assume this is where we look at the bag itself.
Right. Step two is analyzing the packaging geometry. You calculate the external surface area of the bag and the total thickness of the barrier layers. That defines your transfer area and your physical resistance.
And step three is the math. This is where the textbook introduces sorption isotherms, which sounds incredibly intimidating.
It's not as scary as it sounds, I promise. An isotherm simply gives you the mathematical relationship between the concentration of moisture in the air inside the package and the concentration of moisture actually absorbed into the solid food product.
Sounds straightforward enough.
The problem is, this relationship is almost never a clean, straight line. As moisture slowly leaks into the package, the internal partial pressure starts to rise, which slowly decreases the driving force over time. It's a constantly moving target.
So how do you solve for shelf life if the driving force is constantly changing? Do you have to use complex numerical integration software?
You can, but often engineers use step four, a critical conservative assumption. To simplify the math and ensure safety, we assume that the food product acts as an infinite sponge.
An infinite sponge.
Yeah, we assume that every single molecule of moisture that permeates the packaging is instantly absorbed by the food, meaning the concentration of moisture in the air inside the package always stays at absolute zero.
Wait, why do we make that assumption if we know it's not physically true?
Because by assuming the internal air concentration is zero, we are mathematically maximizing the driving force. It assumes the leak is happening at the absolute fastest possible rate.
Oh, I get it. Worst case scenario.
Exactly. This gives you a highly conservative estimate for the shelf life. If your math says the product will survive 6 months under these worst-case scenario calculations, you can guarantee it will actually last much longer. As a plant engineer, you always want to underpredict shelf life rather than overpredict and end up with thousands of spoiled products on store shelves.
Better safe than sorry, but, fully quantified. Now, typically at this point in the deep dive, we do a wrap-up. But since this is a tailored deep dive geared specifically toward process engineering, exam preparation, and real-world plant application, let's do something a little different. Let's run a pre-flight check. I'm going to throw the theoretical concepts at you, and you give me the professor's exam trap or the plant manager's reality check. Sound good?
I love it. Let's run it.
Okay, first up, concentration unit conversions, going from mass density to molar density to partial pressure.
The professor trap here is Fick's law. A classic exam question will ask you to calculate flux, but they will give you the diffusivity constant based on molar density and the boundary conditions in partial pressure. If you don't convert that partial pressure using the ideal gas law and the correct R value, you fail the question. Fluency in these conversions is totally non-negotiable.
Good to know. Next, the physical origins of diffusion. If I have two species initially separated by a partition,
The exam question will ask you to explain this without math. You need to articulate that it is driven entirely by random thermal motion, literally molecules colliding, moving a system from a state of low entropy to high entropy to equalize chemical potentials.
third concept, distribution coefficient, the K value.
On the floor, this is membrane separation. If you are designing a reverse osmosis unit to filter industrial wastewater, your K value dictates what material you construct the membrane out of.
Right, because you want the water, not the pollutants.
Precisely.
Right.
You need a material that has a high affinity, a favorable K value for water, but perfectly rejects the organic pollutants. On an exam, expect to be given a K value and the liquid concentration, and be asked to calculate the exact surface concentration on the solid.
Fourth, effective diffusion in a random porous material using porosity and tortuosity.
The plant reality here is troubleshooting a spray dryer. If a spray dryer is leaving the final milk powder product too moist, the engineer has to look at the tortuosity of the droplets being formed.
Wait, droplets have tortuosity?
Once they start to dry, yes. Are they forming a hard, dense crust too quickly, effectively increasing the tortuosity and trapping the moisture inside? On a test, they will give you the straight line diffusivity and make you adjust it down using the epsilon over tau ratio.
And finally, predicting shelf life.
The biggest operational mistake post-graduation is trusting the packaging completely. Engineers test a new high-density plastic for a month. It looks fine, but at month 6, the product is completely ruined because they underestimated the slow creep of permeability.
Because they didn't use the conservative model.
Exactly. You must use the conservative assumption model we discussed. Assume a constant external partial pressure, assume zero internal pressure, and calculate the time it takes to reach the product's critical mass increase.
So what does this all mean for you, the listener, whether you are staring down a blank exam paper tomorrow or walking onto the plant floor next week? It means mass transfer isn't just arbitrary math. It is the fundamental heartbeat of how matter interacts in our universe.
It really is. Yeah. And to make sure you have the basics locked in, I want you to ask yourself these 3 rapid-fire questions tonight. 1, what 3 factors affect diffusivity? The answer is size, viscosity, and temperature. 2, in coffee extraction, what extracts first and what extracts last? Caffeine is first due to high solubility, organic acids are last.
And the third question.
3, if your K value is greater than 1, which phase holds more solute at the boundary? The liquid phase.
Boom. You are ready. But before we sign off, we want to leave you with a final thought to chew on.
This raises an important question. We spent all this time talking about how to calculate the permeation of oxygen into a plastic bottle over 2 years based on static equations and fixed materials. But how might we design smart packaging? What if we could engineer materials that dynamically change their porosity or tortuosity based on the ambient temperature of the warehouse they are sitting in?
Oh, imagine a package that senses it's getting too hot and actively tightens its molecular maze to fight the leak. That is incredible. Something to think about as you study. Remember, engineering isn't just about passing the test. It's about seeing the invisible forces shaping the world around you, right down to the microscopic holes in a plastic jug. Keep questioning those boundaries. Imagine a grape just cut in half, sitting on your kitchen counter. If you just leave it sitting there in the still air, it's going to take days for it to slowly shrivel up. But if you take a desk fan and point it directly at that sliced grape...
Well, it dries out incredibly fast. You see a completely different physical mechanism at play.
Right, exactly. And that simple, everyday difference between, still air and a blowing fan is really the perfect entry point into our deep dive today.
Yeah, because you're moving from just passive molecular diffusion to active convective mass transfer. The fan changes everything.
It really does. And welcome into the deep dive, everyone. You're sitting in the third seat with us today as we unpack some incredibly dense process engineering concepts. We're talking convective mass transfer, boundary layers, and membrane systems.
Which is a lot to cover.
It is a ton. But whether you're an engineering student staring down a brutal finals week or like a working plant engineer trying to troubleshoot a continuous filtration system, our mission today is to bridge that gap. We want to take abstract textbook math and connect it to real-world physical reality.
And to bridge that gap, I think we have to look closely at what that desk fan is actually doing to the grape.
Okay, let's unpack this. What's actually happening there?
Well, in still air, the water molecules are just slowly wandering away from the fruit based entirely on concentration gradients. It's a passive, purely diffusive process. It takes forever.
Right, but then you introduce flow. You turn on the fan, and suddenly you have fluid physically sweeping those molecules away from the surface.
Exactly. It's flow-enhanced mass transfer. And honestly, that is the heartbeat of process engineering.
Wait, really? Just that simple concept?
Pretty much. Whether you are looking at water evaporating off a piece of fruit or a chemical solute being forced across a massive filtration membrane in a water purification plant, you are ultimately trying to solve the exact same problem.
Which is figuring out the flux, right?
Yes, calculating the flux. You need to know exactly how much stuff is crossing a specific boundary area in a given amount of time.
And that's usually measured in kilograms per square meter per second or moles per square meter per second.
Right.
But, okay, this brings up a massive trap I encountered when I was digging into the source material for this. To calculate that flux, we have to use a value called the mass transfer coefficient.
Oh, yes. The notorious unit trap.
Yes. It is a total headache because the units for this coefficient are constantly shape-shifting. 1 minute, the textbook says it's meters per second, and the next it's something entirely different. It honestly feels like a crap designed to just confuse engineers and fail students.
It definitely feels that way when you're first learning it. But it's actually a built-in mathematical adaptability. It's supposed to be helpful, believe it or not.
Helpful how? Because right now it just looks confusing.
Well, the reason the units for your mass transfer coefficient constantly change is because it depends entirely on how you, the engineer, choose to measure your concentration.
Oh, I see.
Right. So if you measure concentration in moles per cubic meter, the coefficient needs a unit, like meters per second, to make your final Flex equation output correctly. The units have to cancel out.
Okay, so if I'm working with a gas phase system and I decide it's easier to measure my concentration using partial pressure, like in pascals, my coefficient units have to physically morph to cancel out those pascals.
You've got it. It might adapt to pascals or, it might adapt to dimensionless mole fractions. The coefficient is basically this physical property metric that adjusts its own units to balance the underlying math.
So failing to verify your concentration units before just blindly plugging a coefficient into an equation is...
The fastest way to derail a plan design or, bomb an exam calculation. You have to check your units first, always.
That makes a lot of sense. But assuming we manage to avoid that unit trap, how do we actually find the value of this coefficient in the first place? I mean, modeling fluid dynamics down to the molecular level seems like it would require a supercomputer.
It would. And most of us don't have a multi-million-dollar mainframe sitting on the plant floor.
Right. So what do we do instead?
Well, we rarely need one, thanks to dimensionless numbers. Instead of trying to model the behavior of every single fluid molecule, engineers use these dimensionless ratios to scale up small lab experiments to massive industrial pipelines.
Basically relying on empirical data to completely bypass the heavy computational fluid dynamics.
Exactly. We let the decades of experiments do the heavy lifting for us.
Okay, so let's break those dimensionless numbers down, because based on the source material, they seem to form like the holy trinity of mass transfer.
They really do.
Let's start with the Reynolds number. It comes up anytime we talk about flow, but can you give me a physical intuition for it?
Sure. Picture the Reynolds number as a tug of war happening within the fluid itself.
A tug of war between what?
Between inertial forces and viscous forces. So you have the inertial forces, which is the momentum driving the fluid forward, battling against viscous forces, which is the internal friction or, the stickiness holding the fluid back.
Okay, so like water has very low viscous force, but honey has a really high viscous force.
Right. So the Reynolds number just tells us who is winning that internal tug of war.
And the winner dictates the flow pattern.
Exactly. If viscosity wins, the flow is laminar, it's smooth, it's traveling in orderly layers. But if inertia wins, the flow trips into turbulence. It becomes chaotic and highly mixed.
And I'm guessing that shift completely alters your convective mass transfer rate.
Oh, massively. Turbulent flow increases mass transfer significantly.
But just knowing how chaotic the overall flow is doesn't necessarily tell us how the molecules themselves are behaving inside that chaos.
Right. And that is exactly where the Schmidt number comes in. That's our second number. It compares the rate that momentum spreads through the fluid to the rate that the actual mass, the molecules themselves, spreads out.
So it's essentially comparing viscous diffusion to molecular mass diffusion.
Yes, exactly.
Okay, so we have Reynolds and we have Schmidt. What's the third one?
Tying it all together is the Sherwood number. This one compares convective mass transfer directly to diffusive mass transfer.
Oh, got it. So it's basically asking, how much is the fluid flow actually helping us move material compared to if the fluid were just sitting completely still?
Yes. Back to the fan and the grape.
The fan and the grape. I love that. Okay, so to find your mass transfer coefficient without a supercomputer, you just need these three numbers.
Yep. Engineers use incredibly reliable correlation plots based on real-world data. There's a famous linear correlation where you plot the log of the Reynolds number on one axis against a function of the Sherwood and Schmidt numbers on the other.
And it produces a perfectly straight line.
A perfectly straight line. It's beautiful.
So you just find where your fluid's Reynolds and Schmidt numbers intersect on that line, you grab your Sherwood number, and then you just back calculate your coefficient. Man, I love a good empirical shortcut. But speaking of shortcuts, there is a concept here that requires a bit more physical intuition, I think. Boundary concentration.
Oh yeah, this is a big one.
Because to calculate mass transfer, we have to know the concentration of our solute in the bulk fluid, say the middle of the pipe, and the concentration right at the boundary layer, physically scraping against the pipe wall.
Right.
Measuring the bulk fluid in the middle of the pipe is straightforward, but physically measuring concentration at a microscopic boundary layer. That sounds impossible to do without disrupting the flow itself.
It's nearly impossible. I mean, you can't just stick a probe in a microscopic layer without ruining the boundary,
Yeah,
so we don't measure it.
we just skip it.
Sort of.
Hmm.
Instead, we make one of three critical assumptions based entirely on the physical mechanism happening at that interface. We read the physical context to bypass the measurement.
Okay, let's unpack the first one. Say there is a fast chemical reaction happening on a solid surface. What is our assumption there?
Think about the physics of a rapid reaction. If it's practically instantaneous, the surface is essentially consuming the solute the exact millisecond it arrives.
Leaving absolutely nothing behind to measure.
Exactly. So the surface concentration is simply assumed to be zero.
Wow, okay. That feels like a massive pitfall to avoid on an exam. If a word problem says, like, a fast reaction is occurring on the solid surface, you shouldn't sit there hunting for a surface concentration value.
No, you just set it to zero because the surface is eating it all immediately. It saves a lot of unnecessary panic if you just know that rule.
Okay, so that's assumption one. What's the second scenario?
The second involves an absorption sink. So if a solid surface is pulling the solute in, we assume that microscopic boundary layer hits a state of equilibrium saturation instantly.
Like a sponge that's already completely full at the very edge.
Yes. And the third scenario would just be the reverse of that. Evaporation, or mass, actively leaving a surface.
So the underlying logic is identical then. If mass is actively leaving the surface, we assume the immediate interface is saturated, like at equilibrium with the microscopic layer of fluid right next to it.
Precisely. By identifying whether you are dealing with a fast reaction, an absorption sink, or an evaporation source, you completely bypass the need for those impossible measurements.
This theory is really brilliant, but let's anchor it in some actual physical hardware. I want to talk about membrane separation systems.
Do.
Because here's where it gets really interesting. We're forcing a solute out of one fluid, pushing it through a solid barrier into another fluid. We're talking, huge water purification plants or separating delicate proteins in a pharmaceutical lab.
And this is where we see convection and diffusion basically battle it out in real time. The physical geometry of how you build that system dictates whether your plant runs smoothly or shuts down every 3 hours for maintenance.
So let's talk about the standard funnel approach, like pushing fluids straight down into a filter, dead-end filtration. The glaring issue here, based on the notes, is that all the material you're filtering out gets aggressively crammed against the membrane. It just builds up this thick, solid cake.
Yeah, engineers call that the polarization effect. That precipitate cake acts as a massive physical resistance layer. So as it thickens, your transmembrane pressure spikes and your flux just drops to an absolute crawl.
So if you are designing a continuous industrial process, dead-end filtration is just a total trap.
Oh, a huge trap. If you need continuous flow, you'd be facing constant, incredibly expensive downtime to swap or clean those filters.
Which is why continuous operations rely on cross-flow filtration instead.
Exactly. Instead of forcing the feed fluid straight down into the barrier, it flows parallel to the membrane.
Wait, it's the desk fan blowing over the grate again?
It is. That parallel convective flow constantly sweeps the surface, preventing that dense precipitate cake from ever fully forming.
So it keeps that polarization effect highly manageable.
Right. And depending on your target, you deploy different membranes across this really wide spectrum. At the macroscopic end, you have particle filtration.
Which is just like standard sieves catching yeast cells, milled flour, beach sand, things like that.
Yeah, but stepping down from that, you hit microfiltration, which catches much smaller stuff, like bacteria and paint pigments. Then ultrafiltration, catching things like viruses, colloidal silica, and albumin proteins.
And at the absolute smallest scale, we have reverse osmosis, right? Targeting molecular weights around, 100 to 200 Daltons?
Yep, we're talking aqueous salts and tiny metal ions here. And the pressures required to force fluid through an RO membrane are immense.
Because the pores are nearly non-existent.
That, and you are actively fighting against the natural osmotic pressure of the fluid itself. It takes a ton of energy.
Now, when engineers select these membranes, they look at these molecular weight cutoff graphs. An ideal cutoff would be a perfectly sharp vertical line, meaning the membrane blocks 100% of particles above an exact size and lets 100% of smaller particles through. But physical reality is never that clean, is it?
Never. Real membranes have what we call a diffuse cutoff. It's a sloping curve on the graph, not a vertical line. You might block 90% of a target particle, But due to microscopic variations in pore size across the actual physical material, some slightly larger or smaller particles will inevitably slip through.
So you always have to design for that diffuse reality, not the ideal textbook line.
Always.
To visualize this engineering, let's look at how a spiral wound RO membrane is actually constructed. Because it's not just a flat sheet of filter paper, right?
No, not at all. It's an incredibly dense, complex roll. You have the feed solution pushing through a channel spacer, crossing the membrane sheet into a permeate collection layer.
And then the fluid physically spirals inward like a whirlpool until it hits the central collection holes.
Exactly. And the sheer physical forces at play there require heavy-duty engineering. You actually have to cap the entire roll with an anti-telescoping device.
An anti-telescoping device, what does that do?
Well, so the high pressure doesn't just shoot the center out like a cheap paper towel tube.
Oh, wow. I didn't even think about that.
Yeah, industrial RO plants encase these things in massive stainless steel shrouds with perforated steel supporting tubes. The structure has to withstand incredible forces just to maintain the required flux.
That's kind of crazy. But speaking of pressure and resistance, let's talk about calculating it across multiple layers. In a complex system, you might have, say, a liquid film, a solid steel-reinforced membrane, and maybe a gas film on the other side.
Right.
Do we have to calculate the agonizing boundary concentration between every single one of those intermediate layers? Because that sounds awful.
We don't. And this brings up perhaps the most elegant concept in process engineering, the resistance approach. We literally just borrow the math directly from electricians.
Like treating the fluid layers like resistors on a circuit board?
Exactly. When an electrician has multiple resistors wired in series, they don't calculate the microscopic voltage drop across every single millimeter of wire. They just add up the total resistance. Process engineers do the exact same thing with mass transfer.
So we treat the liquid film as resistor 1, the solid membrane as resistor 2, the gas film as resistor 3.
Yep. So total mass transfer resistance simply equals R1 plus R2 plus R3.
That is brilliant. It completely bypasses the need to know the concentration at every intermediate boundary. You just need the concentration at the very beginning of the system and the very end.
And manufacturers make it even easier for us.
Mm-hmm.
For the membrane itself, they won't always give you a complex permeability rating. They'll often just give you a metric called permeance.
What's the difference?
Permeability is a property of the material itself, right? But permeance factors in the specific thickness of the membrane you actually bought. So to find the resistance of that membrane, you just take the number 1 and divide it by the permeance. It's a simple inversion. RC equals 1 over PM.
Wow, that's incredibly straightforward. Let's clarify one more formula, though. How we find the mass transfer coefficient in a lab setting without getting bogged down in reading formulas like a textbook. If I'm running an experiment, I don't need a massive theoretical equation. I just need to measure the physical realities.
Right.
So, if I understand correctly, I take the total mass of the solute I collected and I divide it by my constraints.
Yes. And by constraints, you mean the physical surface area of the membrane you used, the amount of time you ran the test, and the concentration gradient driving the whole thing.
So Ka equals mass divided by the total quantity of area times the concentration difference.
That's it. That relationship spits out your convective mass transfer coefficient, just purely from lab measurements.
Okay, let's try to synthesize all of this. We've covered a huge amount of ground today, from sliced grapes to steel-reinforced RO plants. As a working engineer or an engineering student, what are the situations where you actually apply these principles on a daily basis?
Well, sizing an industrial reverse osmosis plant is a classic application.
Yeah.
Or determining whether dead end or cross-flow filtration is going to precipitate fouling in a new continuous process design.
I imagine it's also crucial when you're looking at a manufacturer's permins data to predict how much solute is actually going to cross a membrane in a given production day.
Absolutely. Or even selecting the right ultrafiltration system to separate proteins without letting viruses slip through due to a diffuse cutoff curve.
Right, managing that curve.
Yeah. And even estimating drying times for an industrial evaporation process that relies entirely on these boundary assumptions we talked about.
This is so practical. Okay, before we wrap up today, let's do a quick rapid-fire review to really cement this for everyone listening. I'm going to throw out a concept, and you give me the punchline. Ready?
Ready.
Starting with the dimensionless numbers. The Reynolds number tells us.
If the fluid flow is laminar or turbulent, who is winning the tug of war?
Love it. The Schmidt number compares.
How fast momentum spreads versus how fast the physical molecules spread.
Okay, here's a tricky one. If a fast chemical reaction is happening on a boundary surface, what do we assume the boundary concentration is?
0. Always 0. because the reaction consumes it instantly.
Why do we use cross-flow filtration instead of dead-end filtration for continuous operations?
To sweep the surface and prevent polarization, you have to stop the buildup of that massive precipitate cake.
And finally, how do we calculate total mass transfer resistance across multiple different media?
We treat them like an electrical circuit in series and just add them up, R1 plus R2 plus R3.
It is incredibly satisfying when complex physics boils down to simple, elegant relationships like that.
It really is. Which actually leaves us with a pretty interesting thought to walk away with today.
Oh, lay it on us.
Well, think about that resistance approach we just discussed. If we can perfectly model incredibly complex physical mass transfer resistances across multiple states of matter just by borrowing the math of an electrical circuit, what other invisible physical hurdles in process engineering could we solve simply by borrowing the math of a totally different discipline?
Wow. It makes you wonder how much of the physical universe is just the exact same equations wearing different clothes.
Exactly.
Well, thanks for sitting in the third seat with us today. Go apply these concepts to that next design challenge, and we'll see you on the next deep dive.